So just a quick reminder, worksheets 2 through 5 will be due on the 6th. Homework number 3 is also due on the 6th, and exam number 3 will be on the 6th. That is next week, Thursday. Make sure to sign in on the sheet. Since we're ahead of schedule, I'm going to get started. Yeah. And thank you to everyone for getting your project topic. Are you not? Okay. So we were talking about volcanoes. Let's talk about the material that comes out during volcanic eruptions. So lava flows occur. Basaltic lavas are much more fluid. So they will generate things that flow across the surface. You get structures that are like, these are a couple of these formed from basalt, much more fluid basaltic lavas. PHY lava, which resembles a twisted or roughy structure, or lava, which has a rough, jagged, blocky texture. These are things that form from the top layer cooling and the bottom moving underneath. And also pillow lavas, which occur along divergent plate boundaries on the ocean floor, where you get, again, the outside cools before the inside. So you get these sort of pillowy structures that form out in round lumps. While andesitic or rhyolitic lavas are much more viscous. Then you get block lavas that are rough and travel shorter distances. What is this? Not working. Plugged in. Okay. So here we have PHY flow. I hope I'm pronouncing that right. And flow. Those are both, these names are Hawaiian because Hawaii has very basaltic lava. So they had names for these types of lavas. PHY flows displaying a characteristic ropey appearance. It's because the top layer cools below before the lower layer does and sort of bunches up. Sort of like this, you know, you can get that skin that forms on fluids. Now pillow lava happens where you get these, you get a sort of a blob of material coming out. It fills up the structure, it solidifies on the outside. The outside gets chilled, and you get new blobs forming. And this builds up over time, and it looks like a bunch of round, pillowy structures. Now, some of the things that come out during an eruption, dissolved gases make up 1 to 6% of magma by weight. These are mainly water vapor and carbon dioxide are the most common gases. There are sometimes other things like sulfur, various sulfur, nitrogen compounds, things like that. So sometimes some really nasty stuff comes out, but it's mostly water vapor and carbon dioxide. And pyroclastic materials. Pyroclastic means basically fragments of fire fragments. These are things like ash and dust, which are fine glassy fragments. Pumice, which is a porous rock from frothy lava that has lots of dissolved gases in it. When the gases release, they bubble up and you get foamy, frothy lava. Lapilli, which are sort of walnut-sized material. Cinders, which are pea-sized material. Blocks, which are hardened or cooled lava. And bombs, which are ejected as hot lava and cool in the air. So a block comes out as a chunk, it cooled before it got thrown out of the volcano, or it hardened before it got thrown out of the volcano. A bomb came out as a liquid and cooled in the air. So blocks are blocky, while bombs are round. So some examples, this is volcanic ash. Particle size is less than 2 millimeters, very fine. It can be pretty nasty because it tends to form by droplets breaking apart and cooling. So a lot of these are sharp, which can do a lot of unfortunate things. Lapilli or cinders are between about 2 millimeters and 64 millimeters. And then you have volcanic bombs, more than 2.5 inches. This is a volcanic bomb. Notice how it's round. And a volcanic block, where it's blocky. So let's talk about the anatomy of volcanoes. A volcano is a place where magma is coming out of the ground and becoming lava. So there's some sort of opening. There's usually an opening at the summit of a volcano at the top, because as the magma comes out, it piles up around it, building up a structure. Often there's a crater or a steep walled depression at the summit that's generally less than 1 kilometer in diameter. If you have something bigger than 1 kilometer in diameter, that's called a caldera. This is produced when the magma chamber underneath the volcano collapses after it empties out. So produced by some sort of collapse following a massive eruption. Volcanoes can also have vents, which are various openings not on the top, on the sides, which are connected to the magma chamber via a pipe, basically. And you can also get things like lava tubes, which are just tubes that lava flowed in. So some general features. Shield volcanoes. We'll start by talking about shield volcanoes. We're going to go through several different types. Some general features. These are the largest volcanoes, but they're not the most dramatic because they're very wide, but they're not very steep. They're broad, they're slightly dome-shaped, so they sort of look like a shield on its back. So they sort of have that arch shape that you might expect from a shield. They're primarily made of basaltic lava, which flows very easily. So they pump out a lot of lava that flows along, and it builds up a big, broad volcano. They get mild eruptions with large volumes of lava, and then mostly begin on the ocean floor and are called seamounts when they're on the ocean floor. So the Hawaiian Islands are all shield volcanoes. And the reason they mostly begin on the ocean floor is because that's where you get this kind of basaltic, you tend to get more basaltic lava there. So here, for example, in the Hawaiian Islands, see how they're broad, but not super steep. They have relatively, you have magma rising up. There's a shallow magma chamber and various things like the summit caldera. And Kilauea over here currently has a oh, I forgot to add that video I found. I'll dig it up and show it to you guys. Lava lake at the top, at its summit, full of lava. Every once in a while, they get big, giant geysers of lava. So actually, feels like something. Let me just show you the video right now. And YouTube.
What you are looking at is a once-in-a-generation type of eruption at Hawaii's Kilauea volcano. On the left, we have lava fountains reaching heights of 1,500 feet or 457 meters from the south vent, while on the right we have tilted lava fountains from the north vent reaching heights of 1,100 feet or 335 meters. And I got to witness this in person, where you could feel the heat from the eruption a full 1.1 miles distant. It must have caused the air temperature at that distance to at least be a full 10 to 15 degrees Fahrenheit warmer. This is where I was filming the eruption, and this is where the two vents were. These twin lava fountains represented episode 35 of Kilauea's cyclical eruptive activity, which has followed this predictable pattern. This means if you start to observe gas pistoning events, the star of the show is only a few hours to days away, while if you see sustained lava fountaining longer than 40 minutes in duration, that peak sustained lava fountaining will soon be occurring. The sustained lava fountaining of episode 35 began at 8:05 p.m. local time on October 17, 2025. As I rushed from Hilo to the eruption site, lava fountain heights from the north vent mid-drive had already reached 500 feet in height. The south vent then activated at 8:50 p.m., soon growing to equal and then greater heights than the north vent. By 9:30 p.m., sustained lava fountains from both vents simultaneously exceeded 1,000 feet in height. True peak lava fountain heights were then reached at 10:15 p.m., achieving a remarkable height of 1,500 feet or 457 meters from the south vent. While this lava fountain was even intermittently taller, it marks the tallest sustained lava fountains a Hawaiian volcano has produced since 1969, a full 56 years ago. In recent times, only the initial stages of the 1969 to 1974 Mauna Ulu East Rift Zone eruption and the 1959 Kilauea Iki eruption reached greater lava fountain heights. I got lucky with the eruption timing and was so happy to witness this spectacle both in person and at night. Just like the other 34 episodes that have occurred at Kilauea since December 23rd of last year, the lava remained completely within the summit caldera, not having the potential to affect any structures. A total of 10 million cubic meters of lava erupted before the eruptive episode ended at 3:32 a.m. on October 18th, marking a stunningly high lava effusion rate of 372.86 cubic meters per second across the 7 hours and 27 minutes it occurred for. The caldera floor level where the eruption occurred also increased by 5.5 meters or 18 feet during this time span. Only 60 more meters to go before part of the area which collapsed in 2018 reaches the height of the upper caldera floor region. While I did say that the lava was completely and harmlessly confined within Kilauea's summit caldera, there was something that did go far beyond the caldera rim, in some cases traveling multiple miles distant. What I'm referring to are various types of tephra which were incredibly lightweight, and Pele's hair, which you can see here as fine golden strands of material. Pele's hair forms when a thin film of lava is ejected upwards as a result of a volcanic bubble bursting during lava fountaining. This stretches small amounts of molten rock originating from the edge of the bubble into incredibly thin and elongated strands of material, and since it cools almost instantaneously, it becomes a type of volcanic glass. This tephra, to the best of my knowledge, did not cause any damage, but was an annoyance to crews who had to clear them off of segments of multiple paved roads. It is currently unknown when episode 36 of lava fountaining will begin, but all signs at the present do point towards another episode happening, with this being possible between October 26 to November 4th of 2025, albeit most likely, in my opinion, between October 29th and November 3rd, 2025. I hope that you found this video interesting, as I definitely enjoyed viewing it in person. As a final note, I would like to thank my new patron Jaden Petkov for supporting my work.
So that was an example of lava fountaining from the volcanoes of Hawaii. Let me just. Oh, okay, so this was the volcano types. That's why, trying to remember why. So, another type of volcano are cinder cones. These are built from ejected basaltic lava, mainly cinder-sized fragments. So because these are all built of the little tephra fragments, they pile up quite steep, but they're relatively small, and they frequently occur in groups. So SB Crater is a cinder cone located near North Flagstaff, Arizona, and these can form quite quickly. There was one that formed in like a field in Mexico, just all of a sudden eruption, building of a volcano. So here is a video about types of volcanoes. Oh, this is about SP Crater, that's right.
This field trip takes us to SP Crater. It's a recent addition to the volcanic activity that began to sweep through northern Arizona 6 million years ago. SP is a particular type of volcano called a cinder cone. These can form very quickly, sometimes in less than a year. They're smaller than composite volcanoes like Mount Rainier, certainly smaller than shield volcanoes like Mauna Loa in Hawaii. SP Crater is composed of unconsolidated cinders that piled up as a steep-sided cone. The crater's still young, and there's not been much time yet for weathering and erosion to wear it down. We'll see how this eruption first produced SP's cone, and then, near the end of the eruption, resulted in a lava flow that emerged from the base. Climbing the steep slopes of SP Crater, you take one step forward and 2 steps back in the loose black cinders. This beautifully symmetric cone, about 30 miles north of Flagstaff, reminded local cowboys a century ago of the shape of a chamber pot, thus the initials SP. As the old wranglers used to say, volcanoes happen. At the top, you're blessed with a breathtaking view of the San Francisco volcanic field, pinyon and juniper grasslands, a broken volcanic terrain that the cowboys summed up as Malpai, bad country. 600 lava flows, cinder cones, and a nearby composite volcano make up this field. It sprawls across 1,800 square miles of northern Arizona. What accounts for all this volcanic activity? The Earth has been hot since the earliest days of its formation. Ever since, it's been slowly cooling off. Hot magma, liquid rock, wells up from deep inside, carrying heat up from below. What do you think happens when magma comes into contact with groundwater? The SP explosion was a doozy. A fiery red fountain shot high into the sky. Peanut and papaya-sized cinders rained back down to build SP's classic cone, 32-degree slopes, 800 feet tall. As the volcano coughed up the last of its magma, a gaping 400-foot crater topped off the cone. The rim was fortified with welded spatter and littered with fantastic volcanic bombs, spindle-shaped rocks that had spun like molten footballs as they flew through the air. Most cinder cones around here are basaltic, but SP is a little different. Its lava tends toward andesite, more silica, and less iron and magnesium. SP's magma was a little stickier than basalt, making it harder for gas bubbles to escape. So when the lava froze, it preserved the shape of the bubbles as a vesicular texture. As magma gets close to the surface, gases that have been trapped within the liquid by pressure can suddenly expand and escape, sometimes violently. Like popping open a shaken can of soda, frothy lava burst out of the volcano's single vent. After most of the gas escaped and the cinder fountains were exhausted, a more languid lava broke out the bottom of the cone. This pattern, cinder cone formation followed by a lava flow, is very common among cinder cones in northern Arizona and around the world. SP's glowing river of lava flowed north 4 miles across open country. It froze in place, forming a prickly rock called lava, more treacherous to walk across than the cone's softer cinders.
Yep. The next type of volcano is a composite volcano. These are the classic steep conical volcanoes that you think of when you think volcano. Like, this is the kind of volcano that a little kid draws. The large classic shaped volcano, thousands of feet high, several miles wide at the base, more or less conical. It's composed of interbedded lava flows and layers of pyroclastic debris, and tends to have violent eruptions. Most are located adjacent to the Pacific Ocean. These are things like Fujiyama, Mount Fuji, Fujisan, Mount St. Helens, various other mountains around the Pacific. So this is Fujiyama, classic composite volcano. You can see this steep conical structure. There's a caldera at the top from where the magma chamber has collapsed. So this is a comparison of the scales of different volcanoes. Here we have the very broad, shallower shield volcano, the nice conical composite cone from Mount Rainier, and here we have a cinder cone, which is steep, but it's also small. So this is a video on the volcano types. This is why I skipped it earlier, because it repeated itself.
Types of volcanoes. There are several different kinds of volcanoes. Generally, differences in magma composition and style of eruption result in different kinds of volcanic peaks. Cinder cones are the smallest kind of volcano. They are steep, cone-shaped peaks built up entirely of pyroclastics. The kind of magma associated with cinder cones varies, but it is often basaltic. Cinder cones may erupt only once or twice before becoming extinct, and few are higher than about 450 meters or 1,500 feet. Shield volcanoes are broad, low-lying peaks that are built up from layer upon layer of solidified fluid lava flows. Basaltic lava tends to be very fluid, and so most shield volcanoes are made up of basalt. Shield volcanoes can become very high, but they are never steep-sided. The Hawaiian Islands consist of a chain of large basaltic shield volcanoes that formed over the Hawaiian hotspot. Composite volcanoes are large, symmetrical, cone-shaped volcanoes. They commonly form from intermediate composition lavas, such as andesite, that contain a moderate amount of silica. Such volcanoes will experience both explosive eruptions of pyroclastics and quiet eruptions of relatively fluid lava. Composite volcanoes build up with layers of pyroclastics ejected by explosive eruptions, alternating with lava flows from non-explosive eruptions. The pyroclastics tend to produce the steep slopes, while the lava flows hold this loose material together. Dome complexes or plug dome volcanoes form from very thick or viscous lavas, such as high silica rhyolite. Lava bulges up from the vent, and the dome grows mostly from below. Because these lavas tend to be slow-moving and sticky, explosive eruptions of pyroclastics are also common. Lava domes occasionally develop within the craters of composite volcanoes when viscous magma moves up into the vent.
And if you want to talk about volcanoes out throughout the solar system, biggest volcano in the solar system, Olympus Mons, is a shield volcano. And there are lots of lava domes on Venus. So let's talk about some of the hazards from volcanoes. I mean, obviously there is lava, but much more dangerous is actually things like pyroclastic flows. So a pyroclastic flow is made of a mixture of hot gases and tephra. So infused with ash and other debris. So it's this hot gas filled with ash and other debris. and it can basically roll down the sides of the mountain, driven by gravity down the slopes of a volcano. This can be at speeds of up to 200 kilometers per hour. So you have this cloud of ash and dust, this sort of wave of ash and dust rolling down the side of the mountain at speeds of like faster than highway speeds. This is what destroyed the ancient city of Pompeii. It was buried by hot ash that got and pyroclastic flows that were blown that direction by the prevailing winds. So here are some images of pyroclastic flows rolling down the side of a volcano. I'm not sure where this volcano is, but as you can see, this is not in the way of those pyroclastic flows. Is not somewhere you want to be. So Pompeii was executed nearly 17 centuries after the CE 79 eruption of Mount Vesuvius. And it was buried in this ash. And it was not the fastest, which means people had time to react to it. But yeah, people got buried in ash and it hardened around their bodies. So their bodies rotted away over time, but the shell of ash that formed around their bodies remained. So there are these like honestly terrifying outlines of people huddling as they were trapped by the ash from this. Another dangerous thing you get from pyroclastics is lahar. This is a mud flow from the interaction between debris and water. So you can get lahars from ice melt, because the volcano gets hotter during an eruption. So the ice melt mixes with the debris, you get this massive volcanic mud flow. But you can also get sudden violent lahars after an eruption, where you get rain, which turns the volcanic debris on the slope into mud, and it flows down the slope. And this is a mud flow, it's debris and water, it follows stream valleys. So here is the lahar flowing down the side of a volcano. I believe this is Mount St. Helens, and this is Spirit Lake. Here is a village buried by a massive lahar. Sort of a different place, I believe. Some other things. You can get tsunamis triggered by the collapse of volcanic landforms into the ocean. Anything that displaces enough water can cause tsunamis. So we have records of certain truly massive tsunamis caused by like landslides and things. The volcanic ash that's generated is really bad for aviation. So you may have seen these things where when the volcanoes in Iceland get more active, planes get grounded across Europe. And that's because volcanic ash, the volcanic material, it basically forms very sharp, pointy pieces of rock, glass or rock, essentially. And it's extremely abrasive. So it's really bad if it goes into an airplane engine. It's very damaging to an airplane engine. Now, volcanic gases, certain poisonous gases can be released from volcanoes. There have been cases of poisonous gas gets released from a volcano, flows down a valley, kills an entire village in history. I mean, we're much better at identifying these now, but there are poisonous gases that get released, they can be inhaled. And the dust and gas can significantly alter global temperatures from massive volcanic eruptions. So in 1815, there was a massive volcanic eruption. I'm going to remind myself what volcano it was. summer. Mount Tambora in Indonesia had a massive eruption in 1815, and in the next year, in 1816, it was like significantly colder because of all the ash and dust that had been thrown up into the atmosphere. And that was known as the year without a summer. It affected crop yields, but it also was like miserable. And in fact, for some bizarre effects, it may have led to the modern vampire story and Frankenstein. Because some English poets and I don't know, I guess they were Gothic romantics or something, were all on vacation in Switzerland that summer. This included Lord Byron and Mary Shelley and several other people. And the weather was so miserable that they decided to stay outside and have a writing contest. And out of that came Frankenstein and what is considered the first modern vampire story, which probably had an influence on the character of Dracula. So here are some volcanic hazards. Lava flows can destroy homes, roads, other structures. Ash and other pyroclastic materials can collapse roofs or completely cover buildings. So you can have lava flows, you can have a pyroclastic flow, you have this cloud of ash. You can get acid rain from that. You can have collapses of lava domes or collapses of flanks, some big landslides, lahars, which are big mud flows. So yes, Tambora in 1815 was volumetrically the largest volcanic eruption to occur in written history. So much volcanic dust was put in the upper atmosphere, the sun's UV energy was partially blocked, and that led to 1816 being particularly cold and being the year without a summer, which then led to, as mentioned, Frankenstein. Mount Pelee in 1902 is located on the island of Martinique in the Eastern Caribbean. It blasted out a deadly cloud of superheated volcanic gas and temper that killed over 30,000 people. Barcuten in 1943, located in Mexico, began as hot gases were emitted in a plowed cornfield. The cornfield was destroyed as this volcanic cone eventually rose over 400 meters in height. Got a volcano kind of out of nowhere. Cinder cone in Mexico. Surtsey in 1963 is located off the coast of Iceland, and this volcanic eruption eventually formed a permanent new island in the North Atlantic, Surtsey. So Freer Heels in the 1990s was located on the Caribbean island of Montserrat. It had been dormant for 400 years until it began spewing ash in 1995. The capital city of Plymouth and the airport were buried in 1997, and most inhabitants left the island, basically rendered most of the island uninhabitable. Mount St. Helens in 1980 is a stratovolcano located in southern Washington state that had been dormant since 1857, and the eruption devastated more than 400 square kilometers of area and resulted in the death of more than 60 people, and it was the biggest volcanic eruption in the US. In the history of the country. I believe, well, definitely in the continental US. There might have been something in Alaska, but most violent. Mount Pinatubo in 1991 was located in the Philippines. It propelled ash into the atmosphere to a height of over 25 kilometers and destroyed thousands of acres of cropland and forced the abandonment of Clark Air Force Base. So now, these volcanic eruptions happen. Why do people continue to live near such a dangerous thing? So like, the eruption of Mount Vesuvius in 79 CE buried the 2,000 residents of Pompeii. It also destroyed several other towns in the area. Yet the large and growing Italian city of Naples lies only a few kilometers away from Mount Vesuvius. Why are people still living there? Well, part of it is that the soils generated from this volcanic ash are really rich and fertile. So, for an example, Naples has amazing tomatoes because of that volcanic soil. So those Italian tomatoes that everybody loves are feeding off the volcanic soil are from Mount Vesuvius. And here is a short video showing a number of volcanic eruptions that were caught on camera.
Volcanoes are scary unless you're immune to lava, ash and falling rock, in which case you're probably not scared by volcanoes. For the rest of us though, they're pretty crazy events to witness. Most of us haven't seen a volcano up close, but thanks to other people and their cameras we're able to see videos of their immense powerful eruptions. We have the best of those for you guys today. My name is Danny Burke and this is the top 10 volcanic eruptions caught on camera. Starting off at number 10 now we have Pu'o'o. This is an active volcano in Hawaii, and in 2014 a lava flow started shooting out eastwards. Roads were closed off as the flow devastated everything in its path. Now, despite numerous defensive measures being taken, it seemed like nothing could halt the slow but steady progress of the lava. This resulted in this incredible footage of the lava burning through a metal fence and then right onto a road. Alright, at the number 9 spot now we have the Sakurajima volcano. This volcano in Japan erupted in February 2016 and some incredible footage was taken of it. The eruption itself was already quite large, sending lava and rock tumbling down the mountain just 30 miles away from a nuclear power plant. However, many people were more amazed at the lightning storms that formed inside the clouds. Lightning and lava, definitely a cool but lethal combination. Next up at number 8 now we have Mount Tabuva. This volcano in Papua New Guinea erupted in 2014. Some tourists were nearby and captured the footage you're about to see. They expected the eruption was going to happen at any moment. They expected that a sonic boom would follow shortly after, but maybe not as loud as this. Next up at number 7 now we have Popocatépetl. This is an active volcano located just southeast of Mexico City. It erupts every few years, and when it did in September 2017, cameras were there to capture it. The rocks it spewed out were found more than half a mile down the slope, as well as ash over nearby towns. Scientists monitor the volcano carefully as 25 million people live within 60 miles of it. A super eruption could be devastating. Alright, at number 6 now we have the Turrialba volcano. This is located in Costa Rica, and the footage you're seeing comes from an eruption in September 2016. It was caught by a research team's cameras, and the footage sped up to show you just how long the volcano was spewing out hot ash. This event consisted of 4 separate eruptions, which led to the closure of the capital city's international airport. It was reported that clinics were filled with people suffering from skin and lung irritations. Some stores even started selling kits with goggles and masks for protection. Moving on to number 5 spot now we have Mount Shindaki. This volcano in Japan erupted in 2015. It was largely unexpected, but amazingly an internet webcam caught the whole thing live. Huge waves of pyroclastic flows cascaded down the side of the volcano, spewing rock fragments and hot gases across the volcano's northwest shore. Japan's meteorological agency raised their alert level to 5 and ordered the island's 140 residents to evacuate. Okay, next up at the number 4 spot now we have the Mayon volcano. This volcano in the Philippines has been known to erupt from time to time, but the most recent event might have produced the most incredible footage so far. On January 22nd, 2018, an alert level 4 was raised as Mount Mayon spewed ash 3 kilometers into the sky. The footage you're seeing right now was taken at night, where lava bombs and rockfall produced a spectacular sight. Now to my eyes, the volcano seems to resemble something like Mount Doom more than anything I've seen in real life. Incredible stuff. Okay, moving on to the number 3 spot now, we have Journey to the Center of the Planet. This clip comes from a BBC documentary of that name, where a scientist in a protective suit ventures to the edge of a volcano's lava lake in order to try and get a sample. Things get a little bit too close for comfort when the lake starts to erupt over the edge, spilling lava everywhere. The scientist has just enough time to get out before lava flows where he was stood just minutes before. Okay, next up at number 2 now guys, we have Mount St. Helens. On May 18th, 1980, Mount St. Helens in the state of Washington erupted. It's often referred to as the single most disastrous volcanic eruption in US history. The whole north face of the volcano volcano just slid away to expose an explosion of molten gas and rock that spread out over 11 different US states. This is the incredible footage from that day. Although some scientists were aware that the volcano was showing increased signs of activity, everyone was surprised at the sheer scale of this eruption. And finally, at number 1 now, we have the Kilauea volcano. Located in Hawaii, it's also referred to as the volcano that never stops erupting, and that is kind of true. The volcano has been erupting since 1983, but things picked up a notch on New Year's Eve 2016 when a lava delta collapsed, taking part of the sea cliff with it. This created a constant flow of lava into the sea below, which has been captured by a number of people, including this footage you're seeing now from the Wall Street Journal. Well, that was fascinating. I always end the video by saying well, don't I? Does anyone else notice that? Anyway, do you like volcanoes? Did this video make you like volcanoes even more? If so, would you like a part 2 to this video? Let me know. My name
So, those were types of volcanoes and some of the hazards from volcanoes. Let's talk about some of the other structures that you can get from volcanic material. So other volcanic landforms. One of these is a caldera. A caldera is a steep-walled depression, generally larger than a kilometer across. And they generally form from the collapse of an empty magma chamber, or they form from the collapse of something underneath the top of a volcano. So the collapse of an empty magma chamber, the collapse of the top of a shield volcano from subterranean drainage, or the collapse of a large area from discharge of large volumes of pumice and ash. So one of the more famous calderas is Crater Lake, which is not actually a crater. This is Crater Lake. It is a caldera that is then subsequently flooded and became a lake, with a small island, Wizard Island, which is in fact a small cinder cone volcano. So you have a magma chamber. Explosive eruption partially empties this shallow magma chamber. Then the summit of the volcano collapses, which enhances the eruption. And then the newly formed caldera will fill up with rain or groundwater. And then you can have subsequent eruptions, could produce a cinder cone like Wizard Island. So here is a short video about how calderas like this can form.
Hi, I'm Dr. Dina. I work with the U.S. Geological Survey in Menlo Park, California, with the Volcano Hazards Program. Today we're going to talk about calderas. When most people think about volcanoes, they think of a triangle shape, and that's what many volcanoes look like. But there are other shapes too, and one of those is called a caldera. What we've done is created a simple experiment to show how calderas form. The experiment uses flour, a piece of tubing with a balloon attached at the end, and a bicycle pump. So what I want you to imagine is that this is the surface of the Earth in an area that's volcanically active. Underneath the surface of the Earth, we're going to inject some magma. When we inject the magma using our handy bicycle pump, it's going to push the surface up. So let's watch. As you can see, the flour is being moved out of the way as we inflate the balloon or add magma to the system. The Volcano Hazards Program has monitoring equipment at different volcanoes to watch ground deformation such as this. In this case, what we're going to do is we're going to pretend that this large amount of magma erupts. To do that, I'm going to let the air out of the balloon, and then we're going to watch to see what happens. So as the air comes out of the balloon, you want to imagine the magma escaping from the magma chamber. Once the magma leaves the magma chamber, there's nothing to hold up the overlying rock. And so all that rock collapses down to where the chamber used to be. So you can see in our experiment, the flour has now collapsed in a somewhat circular shape. We call this shape a caldera.
And if it floods, you get something like Crater Lake. Another sort of structure you can get are fissure eruptions and basalt plateaus. This is where very fluid basaltic lava flows out of cracks, like large, long cracks, and floods large areas. So these are fluid basaltic lava that's extruded from crustal fractures called fissures. An example of these are the Columbia River Plateau in the northwestern United States. And another structure we get are volcanic necks. Volcanic necks are formed when, from the remains of when the magma in the vent going to the top of the volcano solidifies and hardens, and the rest of the volcano erodes away, that neck, the resistant vent that are left standing after erosion removed the volcanic cone, that neck where the magma was rising up, is more resistant to weathering and erosion, and so it remains longer. And so you get basically just the internal vent sticking up out of the ground. So fissure eruptions take place when large volumes of lava get extruded from long fractures along the surface of the Earth. More recently, we've had fissure eruptions in Iceland at, I'm not going to even try and pronounce that name, that has far too many J's, and yeah. Yokel? I don't know. And significant portions of Washington, Oregon, and Idaho are covered with a series of ancient flood basalts that are called the Columbia Plateau basalts. And the Columbia Plateau basalts, the lava that formed them, was extremely fluid, very high temperature, very low silicon content, and eventually covered an area of 576,000 square kilometers and piled up miles deep. So each flood had an average thickness of about 150 meters, and the whole pile is several miles deep. So here are the Columbia River basalts.
2-minute geology, 2-minute geology.
Hello, young people. The Columbia River basalts near Quincy, Washington. We're at Quincy, Washington, but we could pick any spot between Spokane, Washington, and Seaside, Oregon to do this show. These brown layers of basalt are everywhere in the place where the Ice Age floods did massive amounts of erosion thousands of years ago. There's more than 300 layers of basalt here, 300 separate volcanic eruptions, and the stack of basalt is more than 2 miles thick in places. The lavas started erupting 17 million years ago here and flooded a landscape, buried a landscape in lava. The obvious question is, which volcano erupted? Was it Mount Rainier? Mount St. Helens? The answer is none of those. The Cascade volcanoes do not match the chemistry of these basalt lavas. These are lavas that came from the east. They erupted out of fissures, deep cracks, that emitted Hawaiian-like lava starting 17 million years ago. Fissures that formed related to the birth of a hotspot that's now underneath Yellowstone National Park in Wyoming. The present is the key to the past. To really visualize eastern Washington 17 million years ago, we need to go to Hawaii today. Those Hawaiian lavas today are the same kinds of lavas that we have here. Lava flows in Hawaii, very fluid. The most fluid lavas we have in nature average less than 3 feet thick. Here in eastern Washington, the lava flows average 100 feet thick. In Hawaii, the lavas travel on average 3 miles in length. Here in eastern Washington, many of the lava flows traveled 300 miles. And in Hawaii, 30 miles are covered by a typical flow. Here in eastern Washington, 30,000 square miles of area buried. The Columbia River basalts near Quincy, Washington.
It's all out here to see. Coulees, rocks, and canyons is scenery. Right here for you and me. 2-minute geology.
So, these fluid belt, you get these flooding of these basalts. That's the fissure eruptions and basalt plateaus that form. But you can also have volcanic necks. These are these resistant vents that are left standing after erosion removed the volcanic cone. An example is Shiprock in New Mexico. So this is a volcanic neck. This is Shiprock in New Mexico. The idea is that your original volcano, you have a conduit filled with fractured rock and magma in your original volcano. The whole thing gets eroded away, but that tube full of magma is more resistant to erosion and weathering than the surroundings, so it remains. You get something like Shiprock.
Hi, I'm Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the geologic processes that resulted in Shiprock, New Mexico. Out in the western United States, there is a single spot where 4 states come together. These are Arizona, Utah, Colorado, and New Mexico. And right near that Four Corners region is Shiprock, rising up from the desert. This is what Shiprock looks like. From bottom to top, it's a tremendous 510 meters tall, so over half a kilometer above the desert floor, and that's around 1,700 feet tall. What is this mountain? How did it form? Well, we get an answer by going back to our understanding of the anatomy of a volcano. Remember that every volcano has a central conduit through which magma moves up to the surface to erupt. It could erupt as a lava flow, or it could erupt as an explosion of pyroclastic material. What we think happened at Shiprock is that there was one of those central conduits that was erupting material, lava and pyroclastic material out the top, and as that lava moved up towards the vent of the volcano, some of it solidified in that volcanic throat or neck. And because that solid igneous rock was tougher and stood up more to erosion as compared to the layers of lava and pyroclastic material that surrounded it, it ended up basically weathering out in high relief while the surrounding volcano was stripped away. So Shiprock itself, while it's an impressive feature, half a kilometer tall or so, is actually a much smaller part of a larger volcano that existed in the past. When you look at Shiprock today, consider that the magnificent edifice you see there in front of you is actually a small nubbin that was part of a much larger composite volcano in the past. Now here's a question. If you back away from Shiprock, you'll notice that there are a series of ridges that emanate out from the mountain itself. What do you think is the nature of these ridges, given what you know about Shiprock's past? Thank you for your attention. This has been another Smart Figure.
Those are igneous. They're called dikes. That's where you have a crack or a fissure that floods with magma that cools and forms the structure. So that's an example of intrusive igneous activity. So we talked about the extrusive igneous activity, all the stuff that's outside the Earth. Now let's talk about what happens underground. So intrusions, or plutons, are formed as magma rises through the crust. And you can have basically 2 types. You can have sort of irregular, larger extent structures, and you can have tabular structures, flat structures. So tabular intrusive bodies, where magma is forcibly injected into a fracture zone or a bedding plane of rock. If it's a fracture zone, like a fault or a joint, you get dikes, like we saw in that video coming from Shiprock. These cut across bedding surfaces, they're more or less vertical. They're more vertical. If it's horizontal, they travel along bedding planes that are flat sheets. These are called sills. This is when, as the overlying rock is built up in layers, sills are when the magma flows in between those layers. So you can have these tabular intrusive bodies and massive intrusive bodies that have large amounts of intruded material and push stuff out of the way, move things out of the way. The biggest of these are batholiths. These are the largest intrusive bodies. They occur as long linear features. They're often underneath mountain ranges. So many of the mountain ranges that form where oceanic crust is going subducting underneath continental crust have these large batholiths underneath them. So things like the Sierra Nevadas and the Andes, you have these batholiths. They're long linear features often under mountain ranges. There are stocks. This is a smaller pluton, not as big as batholiths, and then laccoliths. Laccoliths are like sills that they're injected between the strata, but enough magma is pumped in between the layers to cause the layers above to sort of bulge upwards and blister upwards. So laccoliths form much the same way a blister forms. So a blister forms when you have fluid between layers of your skin. Laccoliths form when you have fluid magma between layers of sedimentary rock. So here are some examples. So if you have a large magma chamber kind of thing that cools, that forms a batholith, something like a batholith. Magma flowing along faults and joints, that's dikes. When it flows horizontally between layers of the earth, that's sills. If it fills up an area between layers, that's a laccolith. You know, it bulges upwards. So the batholith is this structure, this big structure. So here are some examples of intrusive igneous activity.
This animation shows magma rising toward the surface, feeding two volcanoes and a fissure eruption. Magma is also moving into fractures and between bedding planes. When this subsurface magma cools, it produces intrusive igneous features such as dikes, sills, and laccoliths. A period of erosion exposes these intrusive features, as well as two volcanic necks. Continued uplift and erosion eventually exposes a massive igneous structure called a batholith. Batholiths form the core of some prominent mountain ranges, like California's Sierra Nevada.
So let's talk about where magma comes from. So the Earth's crust and mantle are composed primarily of solid, not molten rock. When things melt, certain conditions have to occur. One of this is partial melting. You get incomplete melting of rocks. This is what produces most magma. You get certain minerals melting out and others remaining. Also, you can generate magma through decompression. So if you have a hot rock under a lot of pressure, if you suddenly release that pressure, it can cause the rock to be able to change from solid to liquid. And finally, when you add water to rock, it will melt at lower temperatures. So when water gets pulled down with subduction in various processes, this can cause rocks that wouldn't be molten before to melt. So the thing is, at the depth of the upper atmosphere, while rock is not in the molten portion, it's very close. So this red curve shows how temperature rises with increasing depth. This is temperature, this is depth. The red area is the partial melting, the yellow area is complete melting. So you can see right here at the depth of the upper atmosphere, stuff is very close to starting to melt. So just a little bit needs to change for it to melt. If you have a decrease in pressure, it effectively moves it up into the partial melting. If you have something that increases the temperature, it can move it to the right into the partial melting. And then if you have something like adding water, that would move the red a little closer and start the melting. So that's why the mantle is mainly solid, but it's very close to being liquid here, which is part of why it flows so easily there. Now, the global distribution of igneous activity isn't random. Most volcanoes are located within or near the margins of plates. The vast majority of volcanoes occur where plates are intersecting with each other, either where plates are pulling apart, causing decompression melting, or where material is being subducted, carrying water in and also moving easier to melt material into warmer areas, causing melting there. So divergent boundaries produce the greatest volume of lava from decompression melting, while convergent boundaries with subduction result in more explosive volcanism. Divergent boundaries produce more mafic lava, more basaltic lava, while convergent boundaries produce more felsic, stickier, gooier lava. Now, there's also some amount of intraplate volcanism. There are places where there are volcanoes that are in the middle of a plate, nowhere near the edge of a plate, like Hawaii, or there's volcanic activity at Yellowstone National Park, for example. These are associated with plumes of heat in the mantle, rising up, causing melting. They form localized volcanic regions in the overriding plate called the hotspot. These produce basaltic magma sources in oceanic crust, like Hawaii or Iceland. They also produce granitic magma sources in continental crust because they're melting the crust, like Yellowstone National Park, which is sitting on another one of these hotspots. I mean, there's no lava coming out of the surface of Yellowstone, but there's all that geothermal activity there. So here are some of the examples of Earth's zones of volcanism. You can have a subducting oceanic plate creating a volcanic island arc. You can have divergence, creating chains of volcanoes from decompression. You can have a subducting oceanic plate under a continental plate, creating a continental volcanic arc. You can have divergence at the surface, down in the you can have divergence in the ocean and divergence on the crust, like the East African Rift Valley on the crust or the Mid-Atlantic Ridge. And then you can also have hotspots, like intraplate volcanism, like Hawaii here, and the Darshan Plateau in India. So this is how plate tectonics and volcanoes are related.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the 6 situations in which plate tectonics influences volcanism. This is a close-up from the middle of the big spread from your textbook that shows these different situations. Volcanoes can be produced in 6 different situations. First is a convergent plate boundary where oceanic crust is being subducted underneath continental crust. A second situation is where oceanic crust is being subducted underneath other oceanic crust. Volcanoes can also be produced at divergent plate boundaries, such as where 2 plates made of oceanic lithosphere are separating from one another, or a spot where a continental lithosphere is rifting apart. Furthermore, we can get volcanoes where hotspots rise through continental crust, or where hotspots rise through oceanic crust. Let's take a look at each in turn. The situation with a convergent plate boundary where oceanic lithosphere meets continental lithosphere is that the subduction of the oceanic lithosphere triggers melting in the overlying mantle, and that produces magma. The magma rises through the crust and ends up erupting at the surface as a continental volcanic arc. The situation with oceanic lithosphere meeting other oceanic lithosphere is very similar. Subduction occurs, mantle melting is triggered, and magma rises up through the overlying lithosphere to erupt at the surface as lava. However, here, what's produced is a volcanic island arc. These 2 types of volcanism are what characterize the ring of fire, the chain of volcanoes that wraps around the Pacific Ocean. We can also get a situation where we have divergence, and that produces volcanism. Basically what happens here is that the crust and the lithosphere are thinned, and that causes decompression melting of the underlying mantle. So we tend to get mafic volcanism here, basically iron and magnesium rich magmas that are derived from the partial melting of the mantle. So this is a situation like we see in Nevada today or in the Great Rift Valley of East Africa. We can also have divergence at oceanic ridges. So here's an example of, for instance, like the Mid-Atlantic Ridge or the East Pacific Rise, where two plates are moving apart from one another, and that basically, again, triggers decompression melting of the underlying mantle. Magma is produced, and it rises up through those cracks to form new oceanic lithosphere. Finally, we have two situations where we can get hotspot volcanism, so a mantle plume is rising up through the mantle and interacting with the base of the lithosphere, and it produces melting that ends up causing volcanism on the surface. So we can have this happen in a continental setting, such as with the Deccan Traps in India or the Columbia flood basalts in the Pacific Northwest. Or we can end up having this situation arise underneath oceanic lithosphere, as is the case with the U.S. state of Hawaii. Now take a look at the North American plate here. You can see that one North American plate boundary is over here in the middle of the Atlantic Ocean, and then we've got another plate boundary, which is a transform boundary down in the Caribbean. There's a subduction zone. Then we've got another transform boundary here, which is the San Andreas Fault, another subduction zone, another transform boundary, and then another subduction zone. We also have hotspot volcanism occurring at Yellowstone and at Hawaii. In terms of where you live, what's the nearest source of volcanism, and which of these 6 types does it fit into? Well, the answers, of course, will vary, but it's a good thing to be aware of. Thanks very much for your attention. This has been another Smart Figure.
And that is the end of chapter 6. So I'm going to stop there for today. Is this? Oh yes. So do remember that the test will be next on chapters 2 through 5 will be next week on Thursday. And if you have not taken the previous test, please get in contact with me to do so.